In this lecture, we will be covering symmetries in polar graphs. Recall the definition of polar coordinates. This gives us an alternative coordinate system for identifying a point, the location of a point in the xy plane. And we think of this, if this is our point xy in Cartesian coordinates, then the way we defined the polar coordinates, or a set of polar coordinates for this point, was by looking at the length of the line segment from the origin O to the point P. We call that R, and the angle formed by that line segment in the positive x-axis, and that is our theta. And so these 2 points together give us polar coordinates for our point P in the plane. Now, we noted that polar coordinate representations of points in the xy plane are not unique, and this came back to the idea that we could add multiples of 2 pi to theta, and by doing so, we're just spinning around and coming back to the point itself. Also, we allow for negative values for r, in which case the point is reflected through the origin. The result of this is the non-uniqueness of polar representations in the of points in the xy plane. And so when we define the idea of the graph of a polar equation, we include all the points P such that P has some polar coordinate representation satisfying the equation. All of its polar coordinate representations don't have to satisfy the equation. You just need at least one. This makes graphing polar equations a little bit more complicated than graphing equations in rectangular. And one thing we often look for to aid us in the graphing process is the idea of symmetries. So the first symmetry that we look at is symmetry about the x-axis. So if this point here is our point r theta, so we know, again, r is the length of this line segment, and theta is the angle between that line segment and the positive x-axis. What does it mean for a polar graph to be symmetric about the x-axis? Well, it means that you can reflect the entire graph about the x-axis. So think of it as whatever you have for a graph in the first and second quadrants, you have a mirror image of it in the second, or in the third and fourth quadrant. So for this particular point here, its reflection down here also may satisfy the polar equation. And if we look at that reflection, we can characterize this in polar. So let's think about how it relates to this point in the first quadrant. Well, the line segment connecting the point to the origin is the same length. So we could characterize it in polar with the same r. And in doing so, we then have to think about the angle made between this line segment and the positive x-axis. And if we do that, we see we do not have theta, but we have minus theta. And the idea here is if both if you have your polar equation and the point r theta and r minus theta both satisfy that polar equation, then the graph of that equation is symmetric about the x-axis. Whatever you draw up here is mirrored down here. For example, consider the equation r equals 1 minus cosine of theta. And we want to check for x-axis symmetry. And to check that, we want to check if the point r minus theta satisfies the equation. So we make replacements. So replace r by r in this case, and theta by minus theta, and see if we can recover the equation. So let's do that. We have our new point, r, and are we going to recover the equation if we replace theta with minus theta? Well, we know that cosine of x is an even function. So the graph of y equals cosine of x looks like this. And it's symmetric about the y-axis, which is a graphical representation of it being even. So if you choose a theta here, and then you look at its mirror image of minus theta on the other side, we see cosine of theta and cosine of minus theta are the same. So again, cosine is an even function. So that means this cosine of minus theta can be written as cosine of theta, which is our equation. So the point r minus theta satisfies the equation, and that means its graph is symmetric about the x-axis. And in terms of graphing the actual polar equation, which we will do in a subsequent lecture, this becomes very handy because anything that you graph, you can reflect about the x-axis. And it saves time and effort. How about y-axis symmetry? So y-axis symmetry would be the case when your point with polar representation r theta is reflected about the y-axis. And let's think about a way to characterize that in polar. So first, we know we have r and theta here. For our original point. And one way we can think of this is to connect this new point to the origin. And we note that the r can be considered the same. This new point has the same distance from the origin. So we can use r But if we think about the angle, this angle, the new angle, which would be this angle here, how does that relate to theta? Well, this theta by the symmetry of these two line segments about the y-axis, we see that the angle between this line segment, our original line segment, and the positive x-axis is theta, but our new line segment and the negative x-axis, that angle between those will also be theta, which means the angle between the positive x-axis and our new line segment is pi. Take away that theta. So this angle here is pi minus theta, and we can use that as a polar representation of our point reflected about the y-axis. And this, of course, is not the only way in polar to represent this point, but it is one. And so we can use that to detect y-axis symmetry. So if you have a polar equation that satisfies the point r theta and r pi minus theta, then anything you graph here in the first and fourth quadrants is mirrored here in the second and third quadrant. For example, suppose we have the polar equation r equals 1 plus sine theta. To check for y-axis symmetry, we're using this point r pi minus theta. So again, if we replace r with r and theta with pi minus theta, can we recover this equation? So let's check that. So can we recover this equation with the point r pi minus theta? So let's make that change. So we plug in, we replace r with r since it's the same, and then we replace theta with pi minus theta, and the question becomes, can we recover this original equation? And we're going to look at this by using our trigonometric identity for sine of a minus b. Sine of a minus b being equal to sine of a times cosine of b minus cosine of a times sine of b. And so this becomes 1 plus, using our identity, pi plays the role of a, theta plays the role of b. We have sine of a, or sine of pi, times cosine of b, or cosine of theta, minus cosine of a, which is cosine of pi, times sine of b, and again b is theta. We know sine of pi is 0, and we know cosine of pi is minus 1. So this becomes 1 plus sine of theta. This string of inequalities was for r, so we see that we recover the equation r equals 1 plus sine theta, which means that the point r pi minus theta satisfies this equation. So r pi minus theta satisfies this equation. Therefore, its graph is symmetric about the y-axis. And the key to this, to using this, is that it saves time. when you're actually doing graphing. Because you can anything you graph, you copy over about the y-axis. The final symmetry that we'll discuss is origin symmetry. And so now here, again, we have our point, our r theta. And if we want to look about its reflection through the origin, this one is fairly natural to see. If this is our r theta, well, one quick way we can do this reflection is by taking this point r theta and multiplying the r by -1 to reflect it through the origin. And so we have minus r theta. So if both the point r theta and the point minus r theta satisfy your polar equation, you have symmetry through the origin. So any point on the graph gets reflected through the origin. And of course, this is not the only way to detect this symmetry. You could take this r theta and you could add pi to it. So you could also check r theta plus pi. Or you could subtract pi from it and do r theta minus pi. There's no unique way to detect these types of symmetries. These are just kind of standard and common ways to detect these symmetries. And again, the way that you would use these symmetries is that it helps you substantially in the graphing process. And the next lecture we'll go into graphing in polar, but the idea is, suppose you had origin symmetry. Then if you graphed something that looks like this, you would reflect through the origin. And so it might take some work to work out this graph. It also happens sometimes when you graph things that you miss entire parts. Just by running through different values for theta, you may trace out part of a polar graph, but not all of it. And exploiting different symmetries allows you to detect other points that satisfy the polar equation that you wouldn't have gotten just by running through values for theta. So this is a technique that's very, very handy, and it's usually a first step when you graph in polar. Look at the equation and see if you can pick up some symmetries. Usually try for at least one, and that helps in the graphing process substantially, and we will look more at polar graphing in the next lecture.